Effect size is another important statistical concept. While the p-value told us about the statistical significance, if the event or the effect just happened by chance or not, right? So if we have a low probability of something happening, usually we reject the null hypothesis and we say that it wasn't due to chance. So that's the statistical significance. The other question is, how big is this effect? How meaningful is it? And that will be the effect size, right? So it could be that we have something that keeps happening consistently, so we have a statistical effect, but it could be very small. Another way to think of it is that the effect size is the amount of explained variation in the dependent variable by the independent variable. So how much does your independent variable explain of the dependent variable? And when we do the ANOVA, we use a effect size called eta squared. In this class we'll be using that one, but be aware that there is a lot more different effect size measures. So for example, partial eta square, omega squared, or also the interclass correlation. Now how do you interpret effect sizes? Here Cohen's has defined some rules of thumb. Small are 0.01 up to like 0.05. Medium is 0.05 up to 0.14. And then more than 0.14 are large effect sizes. Now how do you calculate it? It's quite straightforward. It's the between group sum of squares divided by the total sum of squares. So if you imagine here in this example, 4,700 is the total sum of squares. And now if we want to look at the main effect gender, it's how much variation is explained by gender. It's 200 out of the 4,700 sums of squares. So it's 200 by 4,700 is 0.043, which would be 4% explained variation. At the same time, socioeconomic status is 400 divided by 4,700, so you get the 0.085 or 9% explained variation. The interaction effect, same thing, 300 divided by 4,700 gives you about 6% explained variation. And then the within group effect, right, sometimes called the error term, is 3,400 by 4,700. So you can see here 72% variation is within groups, or is the error variation, right? So that's a random variation that we can't really assign to any of the main effects or interaction effects. So in this example, we could say that SES is the strongest effect, right? While the gender and interaction are a bit smaller. Now, if you look at the table, right, we could add the eta squared as an additional column, and we have here the p-value. And now I would like to point out this example here, the p-value of gender to get a 4.9 with the degrees of freedom associated with gender. Degree of freedom 1 is 1, degree of freedom 2 is 84. Has a p-value of 0.029 and an eta square of 0.04, so we have about 4%, right? So we have a significant effect, and if we would follow Cohen's rule of thumb, we have a small effect size. Now, if we look at the interaction effect, we also have a p-value of 0.029. Well, why do we have that, right? Because the f values here are different. Well, what else changed? The degree of freedom 1. Here it is 2 and 84, so therefore the probability level is 0.29, and actually if you would look at that, the further digits, these two numbers would be different. They're just because of rounding, they're the same. But now we can see both these effects are statistically significant. However, in effect size, you could see the interaction effect, gender SES, is a little bit higher than the gender effect. And then socioeconomic status, highly statistically significant, and also the strongest effect size.